Alright, so today I'm going to actually go into some of the details of the Genesis periodic system and teach you how to start reading and using the periodic table to make predictions about matter, how to balance chemical equations, and just the logic behind the periodic system. So I think the easiest way to begin to learn about the elements is to plot them one by one. And just look at the first 20 elements by themselves so you can get a feel for the logic, because at element 20 it's actually a checkpoint in the system where the numbering logic changes. So the periodic table of elements is a reflection of the number of particles, the number of protons, and the number of electrons in all the elements. So based on where elements fall in this system can tell you how many protons and how many electrons. And electrons, if you know anything about chemistry, you know chemistry is all about the electrons. So the number of electrons in the outermost energy level, the number of valence electrons or outer electrons, is going to tell you how that atom is going to bond with another atom, how reactive it is. It's going to tell you behavior about that element. So the periodic table of elements plots protons, which define what element you have, and it plots electrons, and they add in a 1-to-1 ratio. I know that elements also have neutrons, but the periodic table of elements does not deal with neutrons. Neutrons are not, it doesn't change the element, and neutrons are not really, they don't really have an impact on chemistry. You're not going to really deal much with neutrons until you get to like nuclear physics, where it's more important. And neutrons are actually plotted in the chart of nuclides against, so it's protons on the z-axis and neutrons, or protons on the y-axis and neutrons on the x-axis. But again, that's more for nuclear chemistry, and for today's video we won't get into that. So if you see here, atoms build in a 1-to-1 ratio. So if you notice here, I have this diagram, or here, one proton goes in the middle, and then one electron goes in the first energy level. So if you notice here, hydrogen is in this first spot here, because it's on the first energy level, it's on that first orbital, and it has one electron. And then it's in this first position here because it has one proton. So this is the first energy level here. This n equals 1. This means the first energy level, which is actually an orbital. And then one electron, and that's indicated here with a 1. And then one proton is actually usually the atomic number, which indicates the number of protons, is here in the top right of the box here. I don't know if you can see it, but generally it's there here. You can see it here. And then helium has 2 protons and 2 electrons. Again, it's in that first energy level here. Has 2 valence electrons and 2 protons. Now, in most periodic tables, you're going to see helium over here above the noble gases. The problem with that is that all these elements here have 8 valence electrons. So if you move helium over here, now you can't apply an accurate numbering system. Now something is always going to be off. So we want to place elements based on the universal quantitative data, the universal quantities of particles within the atoms. We don't want to place elements based on behavior, because for the most part, behavior is a function of the number. So the number determines how they're going to behave. So we want to have that quantity as the primary organizing principle of the elements. So this is your first stable bonding rule of chemistry. Hydrogen and helium are anomalies of the periodic table. They don't really fit perfectly anywhere. Helium doesn't really act like any of these elements underneath it. Hydrogen doesn't really act like any of these elements underneath it. They really are in a group of their own. And so the first stable bonding rule is the duet rule, or the 2-electron rule. And that only works for these two elements here. So right away we get our first stable bonding rule. Helium is a stable element. It's a noble gas. It does not react with any other elements. So we see that duet rule happening right here with helium, as it's a stable bond. It doesn't bond with other atoms, and that's your first stable bonding rule. So both of these elements like to form bonds with 2 electrons. So hydrogen in its elemental form bonds with another hydrogen to satisfy that 2-electron rule. The next element, we actually have to move down in the periodic table to the second energy level. So that's why you have 1, 2, and then the third element is below here on the second energy level. And this energy level has enough room to accommodate 8 electrons. So it's in this lithium here is in the first column because it's the third element and it has 1 valence electron. So if you look at this image right here, you see how you have the nucleus in the middle and then the rings that build out like this. So hydrogen and helium put electrons on this first energy level, and then lithium bumps out to this second energy level here and starts depositing an electron on that energy level here. So this gets the third position, again, second energy level. It has 3 protons and 3 electrons, but only one of those electrons is a valence electron. And remember, it's those valence electrons that are important to know for reactivity and behavior of the elements. Remember, so I just said these elements here, below here, in energy level 2, like to form stable bonds with 8 electrons. Lithium has 1 valence electron. So what would you think? Would it be easier for lithium to give away an electron or to take 7 electrons to fill its 8? And you know, that's pretty simple, pretty logical. If it has 1 and it needs to get to 8, instead of taking 7, it's going to give away 1. Okay? And here is where you find your base metals. Base metal in chemistry, by definition, is a metal which likes to donate its electrons, which likes to give away its electrons. And now you move to the fourth element here, beryllium, which adds another proton and another electron. So we see this is in the second column, second energy level. It has 2 valence electrons. It has 4 protons. And how many electrons do you think it has total? right? Remember they add in a 1-to-1 ratio, so this is going to have 4 total electrons, but only 2 of which is indicated here, only 2 of which are valence electrons. Next we move to element number 5 here. This is boron, and boron has 5 protons. It's in the 2nd energy level, and it has 3 valence electrons, 3 bonding electrons, and that's why it's in this position here. You move over one again, this is carbon. It has 6 protons, 6 electrons, but only 4 of those electrons are in the valence shell, in the valence orbital. So it has 4 electrons to bond with. Now, this is a very significant element here. Carbon is the base, it's the backbone of DNA. We're carbon-based organisms here. And the reason why carbon can make complex structures like DNA is because it has 4 spots available to bond with other atoms. It has 4 spots for electrons to receive electrons. So it can make really complex molecules. Carbon actually makes more molecules than all the rest of the elements combined, as far as we know. And then you have nitrogen here, which has 7 protons, 5 valence electrons in that 2nd energy level here. And if you'll notice, this doesn't look quite the same as your regular plot of elements. Even when you would plot the first 20 elements, if you'll notice, columns of elements here are shifted either up or down, so it gives this kind of wavy look here. And there's a reason for that. That is based on an element data point called angular momentum or electron spin. And the electron spin is either up or down. And if you'll notice, all these elements, I call this element shifting, are shifted up slightly. So all these elements here add up electrons. All these elements in this 2nd column add down electrons. And then you can move over here. All these add up, and what you're looking at is the last element relative to the element you're looking at, and its position relative to that element. So if you want the electron spin of boron here, look at the element before that, beryllium, and see where it's located relative to that last element. So it's shifted up, so we know this has an up electron. Carbon shifted up, so we know it has an up electron. Nitrogen shifted up, so we know it has an up electron. Same here. Oxygen has a down electron, fluorine and neon, and also the ones underneath those all have down electrons. And this is very useful in chemistry class when you're doing orbital diagrams. Which orbital diagrams help determine the geometry when atoms are bonding. It helps determine what type of bond you're going to have. So this is an additional data point that can be extracted from the Genesis system of atoms without having to reference a separate chart, which is what the standard practice is now, or having to memorize information. The less information that you have to memorize, and the more information that can just be extracted from the chart at a glance without having to remember all these rules, the easier it's going to be to learn. So, if you see this numbering system is, it goes 1 through 8, and it's based on valence electrons. It's based on outer electrons. So why stop at element 20? Why is element 20 a checkpoint? Well, first, there's actually a few reasons, but first is because when you're plotting the elements one by one, okay, you plot the elements one by one in an unbroken arrangement. So when you're plotting elements, don't have large gaps in the elements that you're plotting, right? You want to plot them in an unbroken arrangement so they're right next to each other. And you can do that until element 21, which goes in between here. And this is where a lot of people get confused, both with the standard periodic table and just when studying the elements in general. They get confused when trying to determine the structures of the transition metals and the rare earth elements, these elements on the inside here. And that's because they don't change the logic of the numbering system. The International Union of Pure and Applied Chemistry just puts this inaccurate, incomplete numbering system on there that doesn't correspond to any useful element data. So in the first 20 elements, we have those 2 stable bonding rules of chemistry, 2 electrons and 8 electrons, okay? These are rules of stable bonding. Remember, the 2 electron rule is for hydrogen and helium only, and then the 8 electron rule is for all elements beneath hydrogen and helium, and all elements here to the right of hydrogen and helium. When you get to element 21, the electrons no longer add to the outer shell. They no longer add to that outermost orbital. Now, atoms add electrons to inner orbitals, okay? So the numbering system logic changes. It changes from valence electrons, which is 1 through 8, to core electrons, which the numbering goes 9 through 18. 18 is another stable bonding rule of chemistry. And then for the lanthanides and the actinides, otherwise called the rare earth elements, the numbering is 19 through 32, and 32 is the final stable bonding rule of chemistry. So your stable bonding rules of chemistry are 2 electrons, 8 electrons, 18 electrons, and 32 electrons respectively. And that is reflected in the Genesis system of atoms, another data point that is not reflected in the standard periodic table. If you notice, the standard periodic table, no matter which one you get, even if you can find one of these wide versions of the periodic table, they never include the rare earth elements in the numbering. And by they, I mean the International Union of Pure and Applied Chemistry, who is responsible for the nomenclature worldwide. They actually set the arrangement and create and apply the numbering system that's used internationally around the world. If you'll notice over here, I have this. This is another periodic table of elements you can get for purchase at webelements.com. This one is ptable.com. You can get this from ptable.com, and you can get this from webelements.com. But again, look, I don't know if you guys can see this, but again, these are excluded from the numbering system. It goes 1, 2, skip all the rare earth elements, and then they begin again at the transition metals, 3 through 18. So again, incomplete numbering system. Obviously something is wrong with this, and the numbering system that they do apply does not actually correspond to useful, accurate element data. It just doesn't. The Genesis periodic system of atoms, on the other hand, it does correspond to useful element data. It corresponds to valence bonding electrons, and then it corresponds to those core electrons in your transition metals and your rare earth elements, which do play a part in bonding. So again, this is just a flat out more accurate, more useful system. And this is the most powerful and important discovery and tool in chemistry. And chemistry is called the central science because chemistry is that foundational science that connects all other sciences.